All right. And as I'm getting this ready, I'm just going to give you a friendly reminder. I had a lot of people that, for better or worse, took advantage of the late cards for homework and would turn in homework after a test was, done. And honestly, like in terms of the policy, that's fine. Like I don't really care. But just thinking about like the purpose of homework, if you wait and do the homework after the test is done, that's not giving you the advantage of having done the practice before the test. So I'm just putting it out there. Just a thought. I will also let you know that it does make people cranky to have to like go back and grade stuff. So, but I'll run with it because I get that sometimes life just happens. I totally get that. But just, just a thought. Just putting it out there as a thing. All right. So if you aren't doing your homework on a regular basis, maybe think about doing it. It's a thing to do. All right. So Razan, you said question 11, is that right? Okay. So here we go. It says, you probably know that it feels better to catch a baseball if you're wearing a padded glove. Explain why this is so using the ideas of momentum and impulse. Go. What does the padding provide you?
Protection from the momentum.
Protection from the... Watch out, there's momentum! Like, is that what you mean? Like, tell me more. Use more physics. All right. If you have answers, your hands are up. I love it. So we're going to go Ian, and then we'll come back to Elizabeth. Is that okay? Go.
So, when you have padding, it increases the amount of time it takes for the ball to actually... Well, it doesn't directly contact your hand, but eventually the ball will contact the glove, which will hit your hand, and it thus lowers the force impacted on your hand.
Absolutely, right? So if we think about, if we literally just think about it in terms of the impulse momentum theorem, we know that F delta T equals M delta V, right? Like we know that that's true. So if F delta T equals M delta V, and we got the same change in momentum, because you've got somebody throwing a ball that you can, and it's got the same mass and the same change in velocity because it's coming at the same speed, and you're going to stop it, right? That's change in velocity. You can either use a big force or experience a big force over some little time, or the bigger that you make this time, the smaller you make that force. Yeah, that's exactly it. Elizabeth, did you have anything to add to that? I totally cut you off. Okay. I don't know if you've ever, my dad grew up in the Chicago area, and in Chicago they play 16-inch softball, with the big ball that looks like this, and they don't wear gloves when they play softball with it's a ball like this, right? And so, but if you watch them catch the ball, when they catch it, do they just go like this and catch it? No, they go like this, right? They bend. Why do they do that? Why do they do all that give? More time, right? You make contact and then you go like this. It's going to slow it down, but it's going to slow it down over a whole lot more time, which means that the force on your hand is much, much, much smaller. Yeah. Does that work? Does that kind of get you where you need to go? Awesome. Other homework questions?
Number 15.
Number 15. So that was problem 15, right?
Yeah.
That's okay. I just wanted to make sure I was reading it right. The safety investigation one. 2 1,400 kilogram cars traveling at 20 meters per second are crashed into different barriers. Find the average forces exerted on the car that takes 1.5 seconds to stop versus the one that takes 0.1 seconds to stop. So this is 15. So you've got a mass of 1,400 kilograms. The initial velocity is 20 meters per second. The final velocity is 0. We want to know the force. And we've got for part A, you got a time of 1.5 seconds. And for part B, you've got a time of 0.1 seconds. Is that making sense?
Yeah.
So I think literally what we're just going to do is solve for F.
Okay, yeah, I just used the wrong formula.
Does that help though? Does that kind of help to put it in perspective? Yeah. Which one's going to be a bigger force? B. Okay. Yeah. They've made some improvements to cars, like before you were born now, but that's really great and it has saved a lot of lives. The big improvement that they've made to cars that's now required in all cars that are created is what?
Seatbelts.
Seatbelts and airbags, right? Airbags is the one I was thinking of. What does an airbag do? Has anybody ever experienced or seen an airbag deploy?
Fly out the windshield. Yeah.
They go out, they do slap you in the face, but, and if airbags deploy inadvertently, they can be, like it can cause problems. Airbags are not like the most safest thing ever, but if you're moving at a high rate of speed, then your body is going to continue, right? Unless a force is acting on it, it's just going to keep going. And if it just keeps going and doesn't have a seatbelt and just keeps going, it's going to hit the dashboard, right? And the dashboard, is it going to have a lot of give? No. And so you're going to have a very, very short amount of time in which to go from really fast to not. Bad, right? Okay? That airbag, just like a big balloon that's filled with air, allows you to slow down more slowly, more time, less force, less death. I mean, like, that's a dark answer, but that's the right answer.
We're gonna get a great point on this, okay?
Yes.
If you don't have a dashboard, you just ride a motorcycle.
Yes.
Then you have lots of time to slow down.
Until you hit the pavement. And then the pavement has no give, right? I mean, like, at some point, gravity is going to pull you down. You will hit something. True.
It's pretty soft.
All right. Other questions on homework before we move on? You good? All right. Okay. We're going to keep cruising. So, I spent all kinds of time last night making really pretty graphs using the some videos that your classmates or you made, and now it's being goofy and won't let me open them. So I'm not gonna like go through. I know, right? It's annoying. I need to go back through and do it and screenshot it. But friends, I want to talk through this with you, and then I'm going to give you just a couple of minutes because I want to make sure that we get to a point where we are comfortable with this concept today. Okay, so in this chart that you have in front of you, hopefully you were able to do analysis for at least one of your videos. I want to just make sure that this is really, really making sense to you. So I want you to think about what the graphs look like. We're going to take a couple of notes here. So pull out your notes because we're going to talk about, in the context of your videos, what we saw. So, in the context of the videos, in the context of the collisions, remember I said that you were going to take videos for 3 different kinds of collisions, or 3, I should say, distinctly different collisions, right? And what were some of the things that you could change to make distinctly different collisions? Yeah.
Using the magnet or Velcro side?
Magnet or Velcro, that we're on the same page right there. Yes, magnet or Velcro. What happens when you use the magnet side? What happens to the 2 carts? They bounce apart. What happens when you use Velcro?
They stay together.
They stick. Those are the 2 like fundamentally different kinds of collisions. All right, so we're gonna name them. We're gonna actually give them like technical names. The magnet kind is called an elastic collision. And the Velcro kind is called, well, it's the opposite of elastic. It is an inelastic collision. Okay? This is one of these times when I really have to make sure I'm enunciating carefully. In an elastic collision, you with me there? In an elastic collision, the 2 carts collide and then they move apart, right? Which means that the 2 carts, the final velocity of cart 1 does not equal the final velocity of cart 2. I'm going to call them carts 1 and 2 today. I don't know why, but I'm just going to call them that. You can call them A and B. You can call them green and gray. I don't really care. Whatever makes you happy, it's all good to me. But the final velocity of cart 1 and the final velocity of cart 2 are not the same. Okay? In that case, and there are multiple ways that you can do this, one possibility is that you have one cart that's going and another cart at the beginning that's sitting still. Okay? If that's the case, I'm just going to draw what that graph is going to look like, that displacement versus time graph. I'm going to make this one red, make this one, what's very distinctly different, blue, I guess. Blue. The velocity of the red car is going to be something like this to begin, right? Up, 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 until the collision. And then depending on the two masses, it might stop or it might bounce back, right? If it stops, what is the displacement versus time graph going to look like at the end? Flat line, horizontal line, right? Does that make sense? Yeah. So it'd be like, oops. Be like that. If you had, hey, bless you. If you had one where it bounced back, then what would it look like? It's going to come down. Does that make sense?
Yeah.
Okay. I'm just going to stick with this one for right now. So the after is going to be just the red one stops and the blue one goes. What is the blue graph going to look like? What is it doing at the beginning?
It's stationary.
It's stationary. So what's that going to look like?
Flat.
Flat line. Then any idea what's going to happen to it after? After the collision, this is the point of the collision right here. What's going to happen to cart blue, the blue cart?
Its distance.
Its distance is going to go, isn't it? Yeah. So it's going to do something like that. That's what the graph would look like if your masses were the same. Okay? If the masses are different, then your slopes might be different too. There are lots of different scenarios. So if it didn't look exactly like this on your graph, that's okay. I just want you to kind of get a sense of what you're looking for. Okay?
It only works if the masses are the same.
The slopes will be equal if the masses are the same. We'll talk about why that's true in a minute. Okay? How are we doing? Are we okay? All right. I'm not going to have you draw more pictures. We'll do more pictures later. Let's talk about the Velcro. That's the inelastic collision. So that's when the two of them are going to collide and stick together. Okay? So let's talk about a story. Well, actually, hold on. Before we do that, what does that mean about the final velocity of 1 versus the final velocity of 2? If they stick together, they're going to be equal, right? Because they're stuck together. They're going at the same speed. So you know that if you have an inelastic collision, that the final velocities of the two are going to be the same. So let's tell a story like that. Let's do one. So let's mix it up a little bit. So here's cart 1. We'll make this one red. And here's cart 2. We'll make this one blue. And I'm going to have this one going slowly and this one going really fast. Yeah, you can tell by the size of the tail lines on them, right? I want you to see if you can figure out, talk to your table mates, what the displacement versus time graph for this one might look like. Imagine that. Talk to your table mates. See if you can come up with what that's going to look like.
Are they going the same way?
They're going the same direction. They're both going this way, but this one's going fast. This one's going slow. We'll say the masses are the same. Yeah. Gut feeling / we maybe saw something like this yesterday. Give it a shot.
Wait, they're heading
in the same direction. So it's going to be like a rear end collision, right? Yeah, the red one's going to rear end the blue one. Super fast.
Probably teach us to like insurance providers.
I'm sure they learned this. Those insurance providers have to learn physics too. So talk to me. What do you think? What's it going to look like? Help me out. I do need a distance versus time. Thank you. Constructive. All right, now help me out. Tell me more. Somebody get me started. You can do it before the collision. What is the red graph going to look like prior to the collision? A steep line? Okay. Tell me about the blue line before the collision.
Not as.
Not as steep? Yeah? It'll start a little higher. Why is it going to start higher? Oh, right. Does that make sense? That's interesting because if you set your y equals 0 or your x equals 0 at the red car, then the blue car's got to start somewhere further away from the origin. Yeah, so that's interesting. All right, so the collision is at that yellow dot. What happens after? It's a line. Tell me about a purple. Okay, I was actually gonna do it in purple, so nice work there. Tell me about the slope of the purple line. What do you think? Is it gonna be as steep as the red one? Is it gonna be as shallow as the blue one? More or less, or in between?
In between.
Oh. In between, cool. So something like that, is that right? Ish? That's not very good. Let me try that one more time. What's that? Is that okay? Yeah. Ish? Okay. All right. So the game is that when you do this, you found your initial velocity, final velocity, you found a change in velocity. The change in velocities aren't necessarily going to be the same. The change in momentum is where the interestingness should happen. So I'm going to give you like 2 minutes, 3 minutes max to talk to your table mates if you have not, or your experiment mates if you have not done so yet, to get the data and compare so that we can make a conclusion, we can draw a conclusion as a class. Okay? Go, go, go. Time's a wasted. Here it goes. Talk.
No, it's not.
So, while doing this, my fingers are crossed. It's always a little bit nerve-wracking, you guys, as a physics teacher, to be like, go collect data and hopefully you get the right answer, right? Yeah. Because labs are never perfect. That's what we know. But walking around and kind of peeking at your answers as at your calculations as you were doing this, what did you notice in these two boxes when you were comparing? What did you know? And it might not be perfect.
They were very simple.
They were very, very...
They're the same, almost the same absolute value.
Yeah, they're very, very close. So I want you to think about this, and we're going to actually write this out. So you want to write this in your notes. You can write it on your lab sheet as well. I'm not collecting this lab. This is a learning lab. That's totally good. I love it, but I want you to write this in your notes. So here we go. I'm going to write my general conclusions right here. Whee! Here we go. So you found that the change in momentum for cart 1, I'm going to call it 1 and 2, the change in momentum for cart 1 was the same as the change in momentum for cart 2, but it was the opposite, right? One was positive, one was negative. Okay? I hope that's what you found. And if that's not quite what you found, then it may have to do with the measurements that you made or whatever, but hopefully you found something similar to that. I'm going to just expand this and make it explode for just a second. Are you ready? It's going to be exciting. So here we go. So we're going to say change in literally means momentum final for the first one minus momentum initial for the first one. is equal to the opposite of momentum final for the second minus momentum initial for the second. This is like the epitome of all like subscript fun. Okay? Here we go. Woo! It's going to be great. I'm going to distribute my negative. So this is going to be negative PF2 plus PI2. Oops. Yep, that's right. Okay. And now what I'm going to do, because I've done this a few times, is that I'm going to put all of the initial stuff on one side. I'm going to put all the final stuff on the other side. Because I know that it's interesting. Okay, so that's why I'm gonna do it. I'm gonna put all the initial stuff over here, but then I'm gonna move it. So here we go. I've got PF1. Hey, it's plus PF2 happens to be equal to PI1 plus PI2. Are you with me there? So that happens to say that the total momentum final has to equal the total momentum initial. This is one of the fundamental laws, rules, things in physics. It is so important. So important that I'm going to put a big yellow box around it. So important that because we got another couple of minutes, don't pack up yet. We're almost there. We got to just kind of process this in our heads. This thing has a name. It's called conservation of, I'm going to put in parentheses here, linear, because we're going to have non-linear later, momentum. Okay? Funny little story. When I was doing my student teaching, I was teaching a class. It was like an honors physics chem class, chem phys. They did chemistry one day, physics the other day, every other day for the year. They were super crazy smart kids. Holy cow. They were like you, but just, 15 years ago. Okay? And my mentor teacher that I was teaching under, he was teaching conservation of momentum, and he had a question on the final. And the question on the final said, give me an example of a time when momentum is not conserved. Crazy smart kids, super smart, probably doctors and PhD physicists now and whatever, okay? They wrote lines and lines and lines. I had the opportunity to grade all of these. And do you know what happened for most of them? I looked at that. If it said more than one thing, crossed it out. It was wrong. What's the right answer? When is a time when linear momentum is not conserved? There isn't one. This is always true. Okay? Always true. Got it? So here's the thing. Trick questions are mean, right? I'm going to give you one thing, and I'm also going to point out to you that you do have homework for tonight. So, actually, I'm not going to give this to you. I'm just going to let you give some problems a shot tonight. They're right here. No. Oh, we got time. I don't know what I was thinking.
Come on.
I know. I want you to take a look at question 1 on this page. Do not lose this because this is part of your homework. We're going to do something class together. What? That's so nice. I'm giving you. Write down the givens for question 1 on this sheet. And I give it to you.
I don't know.
You got 2.
I know that you both.
And that'll be the taking points off for even responding at all.
Yes.
Muppets? She loves the Muppets. Talk to my physics kids. All their questions are about Muppets. All right. The bell's going to ring in just a minute, but not quite yet. I've got 30 seconds. I want you to look at question number 1. I want you to imagine this. With his life jacket strapped on, Gonzo, if you don't know Gonzo, here he is right here, jumps off the front of a canoe that was initially at rest. What does that mean its initial velocity is? 0, right? Here's his mass. There's his velocity after. Are you with me there? There's his velocity. I want to know the velocity of the canoe. Imagine what's going to happen. What's the total momentum at the beginning? I'm standing on the canoe. What is it? 0. I go this way. Where does the canoe go?
That way.
You got it. Okay. The problems you have on your homework are going to look a lot like this. do the problems from the book tonight. We'll work on some of this tomorrow. Does that make sense? Book homework tonight.
So